The quartiles go as a measure of variability with the median. Whenever you report the median as a measure of center, you should report the quartiles as your measure of variability, the interquartile range and the range. The sample standard deviation is going to be the measure of variability that goes when you're reporting the mean as your measure of center. The sample standard deviation is abbreviated with a lowercase s. It's a measure of variability that can be thought of as the average distance of the observations from the mean of a distribution. The standard deviation for the class height data was 4.22 inches. Notice that it gets units just like the mean and the median. You'll understand a little bit better how to picture what a standard deviation is when we get to Chapter 13 and study the normal distribution. For now, we're going to focus on computing it. We have 4 steps in its computation. We're going to find the distance of each observation from the mean, and these are going to be called deviations since they can be negative or positive. So the deviation from the mean, we're going to square each of these distances. We're going to average the distances by dividing their sum by n minus 1. This is called the variance. Since we squared each of the distances, this is in the units squared, so this would be in inches squared. So to get our final answer and put it back on the scale that we collected our data in, we're going to take the square root of the variance to calculate s. Now you may be wondering in step 3 why we divide by n minus 1 instead of n. The reason for that is due to something called degrees of freedom. These are beyond the scope of this course, so you should just memorize for now that we divide by n minus 1 instead of what makes a little more intuitive sense, divide by n. So we're going to divide by n minus 1. Let's do an example and calculate the sample standard deviation using our Mark-Maguire home run data set again. We have the observations listed out in order from smallest to largest. Note that that was just the way that we posted these observations here. They don't need to be in order from smallest to largest because at the end of the day, we're adding together these squared deviations, and addition doesn't care which order you do the addition in. So the first observation in our list is a 9. And so we're calculating our first deviation by taking 9 minus the mean. Remember from our previous calculation, the mean of that data set was 39.92. So we're just copying that number down here again. So 9 minus the mean and then square it gives you 956.05. The second observation in our list is a 9. So again, we take our second observation minus the mean and square it. The third observation is a 22. So we take 22 minus the mean and we square it. And so on and so forth until we get to our last observation. Notice that we didn't waste a lot of time doing the calculations of all those other ones in front of you. We just did them for you, but we saved the last one to do together. So the last observation is a 70. So how are we going to compute this squared deviation? Well, we're going to take 70 minus our mean, which is 39.92. And if you punch that in your calculator and take the square of the deviation, you're going to get 904.81. Now, we've got our squared deviations, and so now we need to average these squared deviations over n minus 1 observations to get the variance. So to get our variance, we need to take all of our squared deviations, so 956.05 plus 956.05 plus 321.13, etc., until we've added all of our squared deviations up, ending with our last one of 904.81, divided by n minus 1. So that's 13 minus 1, since there were 13 observations. And this is going to give you 4439 divided by 12, which is 369.92. Now remember, our units on this are the square of the original units. So you can see home runs squared don't make any sense to us. So step 4 is to take the square root of that variance to obtain the sample standard deviation. So S is the square root of our variance. S equals the square root of 369.92. And if you punch that in your calculator, it should come out to be 19.23. And remember, it gets units, so it's going to be 19.23 home runs. Again, we can't achieve 19.23 home runs in a season. It's not a possible value in our distribution, but we do not round. This is a mathematical calculation, and it's going to tell us about spread in the data, so we don't round it. The following notes about S, the sample standard deviation, are extremely important. These are the kinds of things you want to put on a note card and make sure that you have nailed down tight before you take an exam on this topic. We want you to know these notes. S is used to describe the spread of a distribution when you use the mean to describe the center. Since it describes the spread around the mean, it's the measure of variability that goes along with the measure of center, the mean. S equals 0 only when there is no variability in the data. Let's give an example of a data set that has no variability. What does no variability mean? That means every single observation is exactly the same. So we can just pick any number and repeat it. So if we had a data set that was 5 and the second observation was 5 and the third one and so on, and we computed the sample standard deviation, the spread would be 0. As the observations get more spread out around their mean, S gets larger. Doesn't matter if we add an outlier in the upper end of the distribution or the lower end of the distribution. More spread means a larger sample standard deviation. In practice, we usually use a calculator or computer software to calculate the standard deviation, and many calculators will do it for you. So how do we know if we should choose the mean or the median to report to our audience? Well, the mean is strongly influenced by a few extreme observations where the median is not. If the distribution is symmetric, how do the mean and the median compare to each other? Well, the mean is the balancing point if you were to fill up your histogram with solid material and put a fulcrum under it. In a symmetric distribution, this is also the place in the distribution that has half of the observations below it and half above. So that means the mean, the balancing point, is going to be the same as the median in a symmetric distribution. So we're going to say in a symmetric distribution, they're approximately the same, because we never have exactly perfect symmetry in real life data. But if it's basically symmetric, the mean is going to be pretty similar to the median. If there's a strong skew right, what happens to the mean in comparison to the median? So let's take a look and think about a picture of a skewed right distribution. That's one that has a long right tail. Well, let's say the median's here. If I put my fulcrum there, is that going to balance on a scale? Nope, it's going to tip downwards on this end. You can kind of think of it as somebody sitting really far out on a seesaw. So to pick that seesaw back up, the mean is going to have to go in the direction of the skew to pick that back up. So in a skewed right distribution, the mean is bigger than the median. The mean goes in the direction of the skew. For a skewed left distribution, we have exactly the opposite scenario. In a skewed left distribution, the median might be here, and we'd have to shift the mean down this way to pick up those people sitting way out on the end of the seesaw that are pulling it down on the left side. So in a skewed left distribution, the mean is less than the median. Now you can just memorize those facts for now. That's absolutely fine. We're going to be enunciating them again, reminding you of them again in Chapter 13. So eventually we want you to get an understanding of what's happening in that picture. That will be very helpful if you could do that. But for the meantime, it's fine just to memorize those facts. Now, the standard deviation versus the quartiles. The standard deviation gets larger in the presence of extreme observations. Notice that the mean goes in the direction of the extreme observation, but the standard deviation just always gets bigger if you have extreme observations. It always gets larger. The quartiles are much less sensitive to a few extreme observations. So the moral to this entire story is, if the distribution is roughly symmetric, we're going to want to report the mean and the standard deviation. Remember, once you choose the mean as your measure of center, you should always use the standard deviation with it as your measure of variability. If you have any skewness or outliers, then we're going to report the median and the quartiles. And a way you can do this all at once is by reporting the 5-number summary. So that's fine. Some final thoughts. Numerical summaries do not disclose the presence of multiple peaks or gaps in your distribution. A picture will always help you detect skewness and outliers, so you should always start with a picture of your data. You should always start with a graph of your data.